Uh, so our introduction. In the previous section, we talked about exponential functions. We said if we take a number and raise it to the x power, our exponent can be anything. We can evaluate that. We get a bunch of points. If our base is bigger than 1, we have an exponential growth. If our base is between 0 and 1, we have an exponential decay. Okay. In this section, we will look at functions that enable us to solve exponential equations. An exponential equation is something where we have like, hold on, I'll write it at the top. For example, we have 3 times 1.5 to the x equals 12. So it's an equation where we're trying to solve for the exponent. This is considered a harder problem than evaluating an exponential equation, trying to solve or evaluating an exponential function, trying to solve an exponential equation or solve for the exponent. We have to have a new tools to be able to do this, because we can't just use our previous tools of solving equations, which are adding, subtracting, multiplying, and dividing. That won't work here because our x is stuck in the exponent. So we have to have a way to bring it down. Logarithms allow us to do that. Okay. Logarithmic functions are used to model applications such as investment growth, sound travel, and earthquake magnitude. So logarithms are definitely used in real life to model different situations. All right, the first main thing we're going to practice is writing logarithmic equations and writing out logarithmic expressions. If by chance you have never seen logarithms before, it might look a little bit different to you. We're going to have the word log. Logarithms have bases, just like exponential expressions have bases. There'll be an x, there'll be y. Okay. Every exponential equation has an equivalent logarithmic equation. And our big thing for the first few problems is going to be going back and forth between those forms. We're also going to practice that on our activity for today. Okay, so let's talk about what happens if we start off with an exponential equation. So an exponential equation is something where we know our base, we know the output, we want to solve for the exponent. So here we have 2 to the y power is equal to 3. And we want to be able to solve for y. We want to know what exponent or what power do we raise 2 to get 3. Okay. Logarithms allow us to solve this by, well, a logarithm, I should say, is equal to the exponent. So it gives us the solution to this type of equation. So to solve this equation, we must find the exponent y that makes 2 to the y power equal 3. In logarithmic form, that exponent y is going to be equal to, we read this as log base 2 of x. I'm sorry, log base 2 of 3. Okay, when we see something written as log base 2 of 3, just like I said, the exponential function equation has a base, the logarithmic equation has that same base. The number that we want our output to be equal to, that's where we're taking the logarithm of, and then that's always going to be equal to the exponent. So another little side example here, if we just had the logarithm by itself, something like log base 5 of 7. What does this mean? This means we want to know what exponent can I raise 5 to in order to get 7. Okay. Or in other words, we're asking, if I take 5, what power do I raise it to get 7? So for logarithmic functions, we are given the base is written as a little subscript. We are given the output that we want, and we are trying to solve for the exponent. Okay. So thus, for the 2 to the y equals 3, the equation 2 to the y equals 3 is equivalent to the logarithmic equation y equals log base 2 of x. There are 3 parts in the exponential equation. The base, it's to highlight things again. Y'all know that's my favorite. All right, we have the base of our exponential. That's the same as the base of our log. We have the exponent for our exponential expression. That is what our logarithm is equal to. Logarithms help us solve for the exponent. And then our third number, that's what we're taking the logarithm of. That's what our exponential equation is equal to. So notice how these three parts move when we go from exponential form to logarithmic form. All right, so in general, our rule to go back and forth between exponential and log form, you should write this down, we're going to use it a lot, is that if we have y equals log base a of x, that's the same thing as saying a to the y power equals x. The logarithm tells us what exponent we raise our base to get the number x. Right. Again, write this down because we're going to do a lot of practice with going back and forth between exponential form and log form. And our goal is to use logarithms to help us solve exponential equations. And just so you have a little bit of motivation of why this might be interesting, a simple example we can do is one using maybe compound interest, like the last example we just talked about on the lab. Let's say you're making an investment and you have $1,000. And you know that you want to end up with $5,000. The question would be, well, how long is it going to take me to get to $5,000 if I know my interest rate is, 6%, and I'm compounding continuously? That would give us an exponential equation where we know our starting place, we know P, we know our output, A, we know our rate, but we want to solve for the time t. And in an equation like that, the t would be the exponent. So anytime where your variable is in the exponent, that's an exponential equation, and we'll end up using logarithms to solve it. The little subscript there is the base of the log, where the a is. There are a couple of special bases that have their own notation. For base 10, that's our first special base, log base 10 of x. We just call it log of x. That is the common log. And the second one is log base e of x. We don't write log base e, we say it's ln of x. So it has its own notation, and if you look at your calculators, they have their own buttons. On a graphing calculator, it will be on the left-hand side next to the 7 and the 4. You'll see log of x, that's log base 10, and you'll see ln of x, that's log base e. Oh, and log base e is called the natural log. All right, so the first couple of examples we're going to practice converting exponential expressions to logarithmic equations. Remember, we are taking, let me write it up here at the top, y equals log base a of x. We said that that is equivalent to a to the y equals x. So let's pay attention to where all three of the parts are. First, if we're starting with exponential form, whatever the base of the exponent is the base of the log. So for for 7 squared equals 49, the base here is the 7. So this would be log base 7. We write our base as a little subscript next to the word log. All right, what's next? What are we taking the logarithm of? So there has to be some number here. Sometimes it's in parentheses, sometimes it's not. But there has to be some number here that we're taking the log of. This number is always going to be whatever your exponential function was equal to. So this would be 49. So I know my base, I know my output. What's the exponent? Our logarithm always, always, always equals the exponent. So in logarithmic form, this would be log base 7 of 49 equals 2. And again, the exponent is equal to whatever the logarithm is equal to, or the logarithm is equal to the exponent, I should say. All right. So again, where did all our pieces go? The base of the exponent is the exponential equation is the base of the logarithmic equation. Whatever the exponent equals is what the logarithm should equal. And whatever the exponential expression equals, that's what we're taking the logarithm of. All right, let's do this one more time, or 2 more times. For 3 to the negative 4th power equals 1 over 81. The base here is 3, so we'll have log base 3 of 1 over 81. Again, you can put this in parentheses if you want to. Occasionally, I hear people read this as log 3 to the 181st power? No, that is not an exponent. The 3 is a subscript, it's a base. The 81, 1 over 81 tells us what we want our output to be. Okay, so this is saying if I take 3 as my base and I want to get 1 over 81 as the output, what should the exponent be? The exponent is -4. So the logarithm equals -4. And last one of these, 10 squared equals 100. Our base here is 10, so this would be log base 10 of 100 equals 2. And this is almost correct, except, scroll up a little bit. Remember, log base 10 has a different notation. That's the common log. For the common log, we do not write this 10. You're just going to write log of 100 equals 2. All right, and I just want to highlight one more time where each of these pieces go. That is not the highlighter. The base of the exponential equation is the base of your log. Okay, the exponent, this is the biggest part. Whatever the exponent is, that's what your log equals. By definition, this is what the logarithm gives us, the exponent. And then the number that you're taking the logarithm of is what the output is here. All right, we get to practice this in our first example. All right, you guys, let's go through all of these. For practice exercise 1, again, we're doing more converting exponential functions to logarithmic equations. Pay attention to where your base goes, where your exponent goes, and where the other number, which your exponential equation is equal to, goes. For part A, 3 squared equals 8. You should get I'm sorry, I lied. 3 squared is not equal to 8. 2 cubed equals 8. This would be log base 2 of 8 equals 3. For part B, 16 to the 1/2 power equals 4. This would be log base 16 of 4 equals 1/2. For part C, 4 to the -3rd power equals 1 over 64. This would be log base 4 of 1 over 64 equals -3. A couple things about notation. Again, sometimes you'll see parentheses around these numbers. If you type this into your calculator, usually a set of parentheses pop up, okay? Other thing, and I'm gonna keep on pointing this out, the logarithm is equal to the exponent. These things should always match, okay? For parts D and E, they work out the same way, but notice for part D, we have a base of 10, and for part E, we have a base of E. And base 10 and base E logarithms have their own notation, the common log and a natural log, okay? For base 10, remember, we just don't write the 10. So log base 10 of, 10 to the -3rd power equals 0.001. This would be log base 10, which is just log, of 0.001 equals -3. And for the last one, e to the 0 power equals 1. For log base e, we use the notation ln. So we'll have ln of 1 is equal to the exponent there, which is 0. And again, our exponents are equal to the logarithms. All right. So now that we know how to write exponential expressions in logarithmic form, for the next example, we'll go the other way, writing logarithmic equations in exponential form. For these, I feel like they're a little bit easier because when you write your equation in exponential form, it should make sense, okay? So you should get something that is true. So it's really easy for you to check if you mix up the numbers. For instance, for part A here, log base 3 of 81 equals 4. Our base is 3. Whatever the logarithm equals is our exponent. So this is 3 to the 4th power. And what's 3 to the 4th power? 81. Excuse me. That checks out. If you were to accidentally mix this up then the only way you can really mix it up, you might have 3 to the 81st power equals 4. Does that make sense? Clearly that's wrong. So it's kind of easy to check your answers here because we know that the exponential equation that we get should be true. All right, so log base 3 of 81 equals 4 gives us 3 to the 4th power equals 81. For part B, log of 1/10 equals -1. This is 10 to the -1st power, because log written without a base, we know that the base is 10. That's the common log. Okay. Whatever the logarithm equals, that's our exponent. And then this other number goes here. So 10 to the -1st power equals 1/10. Again, that is true. And then the last one, ln of e equals 1. ln is base e. So this one might be a little bit weird for you. If it helps, remember ln is log base e. So this is saying log base e of e equals 1. That would be e to the 1st power equals e, which is true. There's the one. So in our next set of practice problems, we're going to practice writing a logarithmic equation in exponential form. We have 4 logarithms here, and we want to try to write them in exponential form. So the base of the log is the same as the base of the exponent. Whatever the logarithm equals, that's what your exponent should be equal to. And then the other number is what the exponential equation should be equal to. All right. Let's start here with problem A. Log base 4 of 16 equals 2. Again, the base of the log, the little subscript, the 4 in this case, is the base of our exponential expression. Whatever the logarithm equals, that is our exponent. And then you could do this even without knowing the other number. What's 4 squared? 4 squared equals 16, and 16 is the other number. So 4 squared equals 16 is exponential form. For log base 25 of 5 equals 1/2, this would be 25 to the 1/2 power equals 5. Again, check these to make sure they make sense. 25 to the 1/2 power is the square root of 25. That does equal 5. For part C, log of 0.01 equals -2. This is the common log because no base is written here. So that's 10 to the -2nd power equals 0.01. That's true. That's 1/100th. Okay. And then ln of 1 equals 0. Again, ln is base e. So this is e to the 0 power equals 1. And again, in exponential form, the exponential equation that you get should be true. All of these are true. E to the 0 power is 1. 10 to the -2nd power is 0.01. 25 to the 1/2 power is 5, and 4 squared is 16. All right, now that we've practiced going back and forth between logarithmic form and exponential form, next we want to practice actually evaluating logarithms. So what if all 3 of the parts aren't there? What if we're just given the base and we're just given the output and we have to find the exponent? How do we actually evaluate these? Okay, using your calculator for the most part. For most of the logarithms, well, let me say it this way before we jump to that calculator section. For some logarithms, we might be able to solve them without a calculator. For instance, if we have log base 3 of 9, what power would I raise 3 to get 9? Well, 3 squared is equal to 9. Or log base 2 of 64. What power would I raise 2 to get 64? Well, 2, 4, 8, 16, 32, 64. That would be the 6th power. Okay. Let's do another one. Log base 1/2 of 4. Now that one's interesting. What power would I raise 1/2 to get 4? So 1/2 to what power equals 4? Well, I know that 4 is 2 squared. And then if I flip that base, that's 1/2 to the -2nd power. So if I raise 1/2 to the -2nd power, I get 4. So this logarithm would equal 2. If your base and the output can be written in terms of the same base, or another way to think of that is if this number is a power of your base, then you can solve these logarithms without needing a calculator. But if I easily just change one of the numbers, you can see that most of the times these logarithms are going to be equal to decimals. So if I change log base 3 of 9 to log base 3 of 10, what power do I raise 3 to get 10? I don't know. I know 3 squared is equal to 9. I know 3 cubed is 27. So something between 3, something in there. Those would be our answers, okay? And again, we can use our calculators to help us solve that. Okay, so that brings us to here. Use your we can use our calculators to evaluate logarithms that are in terms of the common log or the natural log, because those are the buttons we have on our calculator. All scientific calculators will have those, okay? For other things, okay, if our base and the number that we're trying to take the log of can be written in terms of the same power, or if that number is our base to a power, we can evaluate the logarithm without needing a calculator. So for log base 2 of 16, what is that equal to? We can write this in exponential form and we get 2 to the x power equals 16. That should be easy for us to figure out. We know that 2 to the 4th power equals 16, so x would be equal to 4. Okay? In order to help you simplify these types of or evaluate these types of logarithms quickly, it might be helpful for you to just remind yourself or make a list of the first few powers that you know. Like we know 2 to the first power is 2, 2 squared is 4, 2 cubed is, these numbers look awful, 4, 2 cubed is 8. Okay, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, and so on. 3 to the 1st is 3. Well, we know the first powers. 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81, 3 to the 5th would then be 81 times 3, 243. Okay, we know our first several squareds. 4 squared is 16, 5 squared is 25, 6 squared is 36. Use these properties of, or these exponential equations that you know to help you solve logarithms. All right, let's jump into our examples. So this is example 3. We'll go through these 4 together and then jump into practice problem 3. All right, for log base 2 of 8, if it's helpful for you, you can always say, oh, this equals, I'm sorry, not 0. This equals x. And then you want to convert these to exponential form. I'm going to use a different color. Let's go purple. All right, so in exponential form, this would be 2 to the x power equals 8. And then you ask yourself, well, what power do I raise 2 to get 8? We should all know that 2 cubed equals 8. So x equals 3. Okay, what does that mean for the logarithm? Log base 2 of 8 equals 3. All right, and we can use the same kind of idea for the rest of them. Log base 3 of 1 over 81 equals x. This is 3 to the x power equals 1 over 81. For 1 over 81, we know that 81 is 3 to the 4th power. So this is 3 to the x equals 1 over 3 to the 4th power. And then using properties of exponents, we can write this as 3 to the x power equals 3 to the negative 4th power. 1 over 3 to the 4th power is the same as 3 to the negative 4th power. And then here, this is very important. If the bases are equal, then the exponents here have to be equal as well. So x equals -4. Or we can say this logarithm, log base 3 of 1 over 81 equals -4. Okay. Next, part C, log of 100 equals x. Remember, if there's no base written, our base is 10. So this is saying 10 to what power equals 100 in exponential form? We know that, this one isn't too bad. 10 squared is equal to 100. So x here is equal to 2, or our logarithm, log of 100 equals 2. And last one, the ones with E are always interesting looking, because this one's it's super easy, you'll see. ln is log base E. So this is saying E to the x power equals E to the 5th power. Well, our bases are both E there, so that means our exponents must be equal. X is equal to 5. So ln of E to the 5th power is just 5. It's a nice little property of logarithms there, actually. So for the next example, or group of practice exercises, I should say, you want to try to rewrite each of these in exponential form, and then from the exponential form, that'll help you solve or evaluate the logarithm. Okay, let's knock this one out. So we've written this in exponential form. Log base 5 of 625 equals x is 5 to the x power equals 625. 625 is 5 to the 4th power. So that means x is equal to 4. Or this logarithm, log base 5 of 625 equals 4. All right, for part B. Here I go with all my typos, messing things up. For part B, log base 2 of 32 equals x. This would give us 2 to the x power equals 32. And then that's when we think about our powers of 2. 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. So 32 is 2 to the 5th power. That means x equals 5, or log base 2 of 32 equals 5. Next, we have log of 10,000 equals x. 10,000, or if we write this in exponential form, we'll have 10 to the x power equals 10,000. Okay, for 10 to the x power equals 10,000. 10,000 is 10 to the 4th power. It's easy when you have a number like this, one with a bunch of zeros. Count the number of zeros, and that tells you what your exponent should be. So this is 10 to the 4th power. X is equal to 4, or we can say log of 10,000 equals 4. And last one, ln of e to the 5th. This would be e to the, we just did this one, e to the x power equals e to the 5th. So x is equal to 5, or ln of e to the 5th equals 5. It is true that ln of e to any power equals the power. So if you see that one, that's a rule of logarithms. You can use that. We talked a lot in the last class about the graph of an exponential function. Just to recall on the side here, for exponential functions, we said we get either an exponential growth that looks something like this, or an exponential decay that looks something like this. We said that the domain is all real numbers. The range is 0 to infinity. There's a y-intercept, and then there was a horizontal asymptote. Logarithmic functions are the inverse of exponential functions, so we're going to end up getting the exact opposite of this graph. The domain and the range are going to switch. Instead of having a y-intercept, we're going to have an x-intercept. Instead of having a horizontal asymptote, we're going to have a vertical asymptote. In the next example, we'll look at the graph of a logarithmic function. Okay, so to sketch the graph of a logarithmic function, we're going to start off with log of x, which is a base 10. We're going to create a table of values and then plot the points and then connect the points to see what the graph looks like. All right, so we're looking at 10 to different powers to help us with this. Okay. So for table, or in table 1 and table 2, I should say, table 1 gives us the exponential form of 10 to the x. And for table 2, we're going to switch the inputs and the outputs because they're inverses of each other. And that'll give us the table for log of x. Okay. So when x is equal to -1, for 10 to the x is equal to 0.1, that means for the logarithmic function, when x is equal to 0.1, log of 0.1 equals -1. So notice the inverse relationship we have there. They're opposites. And I just want to emphasize here what our numbers are that we're plugging in. So our input is -1. I'm sorry, our input is 0.1 and the output is -1. When our input is 1, our output is 0. When our input is 10, our output is 1. Okay. If we plot just those couple of points, you can, of course, plot a few more as well. Let the inputs be any power of 10, and then the outputs will be the actual exponent. So if we wanted to make a few more points in the table, if we're looking at log of x, let's say our inputs are 10, 100, 1,000, 10,000. Then log of 10 is 1. Log of 100 is 2. Log of 1,000 is 3. Log of 10,000, we just did that one, is 4. So we get the points 10, 1, 100, 2, 1,000, 3, 10,000, 4. Notice the inputs are changing pretty quickly. The inputs are getting really, really big, and the outputs are just going up by 1. Okay, so that means this function is growing, but it's growing pretty slowly because the outputs are only going, the inputs are growing really quickly, and the outputs are barely even moving, just by 1. So we end up getting a graph that looks like this. Okay, as x gets more and more, or closer and closer to 0, I should say, the function is going to get, sorry, I'm on highlight here. The graph of the function is going to go down to -infinity. So we end up having a vertical asymptote here. Notice this graph crosses the x-axis at 1, 0. And then the graph does increase, but it just increases very slowly. Okay. So notice if we look at this graph, the graph rises from left to right. So it's increasing. It does not intersect the y-axis. So like I said, there's an asymptote there. And we've pointed out where the intercept is. Okay. I'm going to skip. What? Oh, this is just showing that there's an asymptote. So if we look at the table of the function, we will see as x gets closer and closer to 0, we definitely have an asymptote. I want to talk more to that though. So let's think about what happens as we take 10 and raise it to negative powers, I should say. 10 to the negative first power is 1/10 or 0.1. 10 to the negative second, 0.01. 10 to the negative third, 0.001. 10 to the negative fourth, 0.0001. So what's happening here is these outputs are getting closer and closer and closer to 0. When we think about the inverse of that, so for log or y equals log of x, when x is equal to 0.1, we get -1. When x equals 0.01, we get -2. When x equals 0.001, we get -3 for y. When x equals 0.0001, we get -4. So this table here shows us what's happening in our graph. As the x values get smaller and smaller and smaller, closer to 0, we should say 0.1, 0.01, 0.001, 0.0001. As they get closer to 0, the y values are becoming more and more negative. Okay, that's what's happening here. So a few properties we should notice about this. Again, one, this one's ln of x, but it's the same general idea for the general graphs of logarithmic functions. If our base is bigger than 1, we're going to get a graph that rises from left to right. The domain of a logarithmic function is 0 to infinity. So what does that mean? We cannot take the log of a negative number. We can't take the log of 0. We can only take the logarithm of positive numbers. Notice how this is opposite from what we have for exponential functions. Here, the range is -infinity to infinity. They switch from what we saw for exponential function. There is no y-intercept, but we do have an x-intercept at 1, 0. And there is no horizontal asymptote, but we do have a vertical asymptote now at x equals 0, the y-axis. So if you compare the graphs of exponential functions and log functions, you'll notice that they are exact opposites. I want to write them both together here, even though that's what's written here, but I just want to write them again together. So let's compare exponential versus logarithmic. And in both cases, we're looking at a being greater than 1. So if you have y equals b to the x versus, is this written in general or just for log base a of x? Okay. And then y equals log base b of x. How will these two graphs compare? What's going on in my house? All right. For the exponential one, we know that we have an exponential growth here. The graph looks like this. Our y-intercept is here. Cool. For the logarithmic function, it's basically the reflection of this graph over the line x equals y. So our graph will look like this. And we have an x-intercept here. Okay, so let's go through the things. For exponential, the domain is -infinity to infinity. The range is 0 to infinity. For logarithmic, the domain is 0 to infinity. The range is -infinity to infinity. It's bothering me that that's not going. All right, our exponential function has a y-intercept at 0, 1. Exponential function has an x-intercept. I'm sorry, said it backwards. Exponential is y-intercept at 0, 1. Logarithmic has an x-intercept at 1, 0. Vertical asymptote is a vertical line, so it's x equals 0, which is the y-axis. Horizontal asymptote, the horizontal asymptote is a y equals 0, which is the x-axis. So these graphs are exact opposites of each other because the functions are inverses. The domain and arranger switch. One has an x-intercept, one has a y-intercept, one has a horizontal asymptote, one has a vertical asymptote. Practice problem number 4, where we talk about determining the domain of a logarithmic function. The domain is all possible x values that can be plugged into the function. For a logarithmic function, we said that we can't, or I said it a few minutes ago, we cannot take the logarithm of a negative number or 0. So for us, we're going to take this term that we're taking the logarithm of, and we know that that has to be greater than or equal to 0. I'm sorry, greater than 0, strictly greater than 0. And then that gives us our domain. So for 2 times log of x, we know x has to be greater than 0. So that means that the domain is 0 to infinity. Pretty straightforward. For log of x minus 3 has to be greater than 0. So the domain is x is greater than 3. This would be 3 to infinity. Really quickly, why does this change? Didn't we just say that for a logarithmic function, the domain is 0 to infinity? That is if the logarithmic function is of the form log base a of x. Here we don't just have x, we have an x minus 3. So that's going to shift our domain a little bit. Similarly, for part C, we don't just have x, we have an x plus 3 that we're taking the logarithm of. So that x plus 3 has to be greater than 0. That means x can be any number greater than -3. So our domain is -3 to infinity. Again, you might be thinking, well, I thought we couldn't have negative numbers. The term that you're taking the logarithm of can't be negative. So if we plugged in a -2 for x here, g of -2, this would be 2 times log of -2 plus 3 minus 5. This becomes log of 1. That's perfectly fine because that's a positive number. If that simplified to a negative number, then we would have a problem. Sorry, -5. We can actually evaluate this too. This would just be -5, but you weren't asked to do that. I just wanted to show that you can evaluate some logarithms at negative numbers as long as this term, or more specifically, this term doesn't become negative. Last one, some applications of logarithmic functions. I'm just going to jump straight down to the, this is a good one. So one fun one that I think, and you'll see it on a couple of the examples, is how we measure things on the Richter scale. You know, every time there's an earthquake or something, we say, oh, it's a 6.5 or 1.2 or 3.9 on the Richter scale. San Francisco experienced an intense earthquake with a magnitude of 7.8 on the Richter scale. In 2014, Los Angeles experienced a moderate earthquake measuring 5.1 on the Richter scale. Compare the intensities of the two earthquakes, okay? Let's convert the magnitude of both earthquakes to intensities using log formulas, okay? So our formula here is R is equal to log of I. That means the measurement on the Richter scale is equal to the log of the intensity. I stands for intensity. The R is the numbers that we're used to seeing on a Richter scale. So in this case, we're saying that if something measures a 7.8 on the Richter scale, 7.8 is equal to the log of the intensity, and the intensity would be 10 to the 7.8 power, okay? Whereas if we compare that to the, that one was in 1906, if we compare that to the 2014 earthquake, which was a 5.1, the intensity there, if we write in exponential form, will end up being 10 to the 5.1 power, okay? Then the question is, we want to compare the intensities, so we can just divide the two to see how many times stronger the 1906 earthquake was compared to the 2014 earthquake. So if we take 10 to the 7.8 power and divide by 10 to the 5.1 power, that gives us 10 to the 2.7 power. And if you calculate that, that's about 501. So what does this mean in terms of the intensity? The intensity of the 1906 earthquake is 501 times greater than the intensity of the 2014 earthquake. So it's a lot more intense. So when we look at things on a Richter scale, going from like a Richter scale of 5 to 6, that changes a lot. That means it's a lot more intense. Okay, and again, the way that we compare the intensities is to divide them. Let's do one example here. Practice example 5 deals with decibel levels. Use the formula D equals 10 log of I over 10 to the negative 12th power to determine the decibel level of a dishwasher with an intensity of 10 to the negative 7 watts per square inch. Okay, so D would be equal to log of, I can't read, 10 log of, we're told I is 10 to the negative 7 over 10 to the negative 12th. And then we can simplify this. This is 10 log of 10 to the negative 7 minus negative 12, so plus 12. 10 log of 10 to the 5th power. And then this is where the fun comes in. We can evaluate log of 10 to the 5th, okay? This is asking 10 to what power equals 10 to the 5th? X would just be equal to 5. So this entire expression equals 5. And we get 10 times 5, which is 50, okay? So this dishwasher has a decibel level of 50 decibels.